Okay, we're going to get started. Welcome to the Australian Club of Acronyms April meeting, and I thank everyone for coming out. Our guest speaker today is Dr. Cyrus Taylor. He's a professor of physics at Case Western University, and last year Dr. Taylor came out and talked to us about particle accelerators. It was very exciting talk. This afternoon he's going to talk to us about global warming. So please, let's have a hand for Dr. Taylor.
Thank you very much. Oh, yes. Is that too loud?
No.
Yeah, okay. Great. So it is a pleasure to be back. And I'm talking on a rather different subject today. The stuff I talked about last year is the kind of thing that I've spent most of my career working on. But for the last 5 or 6 years, I spent most of my time working on issues related to climate change. And just to make sort of a personal connection on it, when I got my PhD in 1984, I spent 6 weeks bumming around East Africa. And one of the things that I had set out to do was to climb Mount Kilimanjaro, which is the highest mountain in the world that you can just sort of walk up. It doesn't require any technical ability. And so this is a photo of Kilimanjaro from Moshi, about 20 miles away from the base of it, in July 1984. And I didn't climb it then because I came down with malaria instead, and didn't go back again until 2017.
Wow.
My daughter had been in Tanzania the year before, working in Olduvai Gorge, and she'd seen Kilimanjaro from the airplane, and so the next year she called me up and said, "Dad, if we're ever going to climb Kilimanjaro, we should do it now, because we might not both have time again." So we went, and when we arrived at the foot of Kilimanjaro, basically the same spot a few miles away, it was cloudy, but the next morning the clouds had lifted, and that's what the mountain looked like then.
Ooh.
And what do you notice about the change?
A lot less white.
Yeah. The white on the top left were glaciers on the side of the mountain, and they're almost all gone 33 years later.
Same time of year?
Yeah, it's same week of the year, actually. And so, roughly 80% of the ice volume that had been there in 1984 was gone by 2017. And that was kind of a wake-up call for me. And so I had thought last year when I talked about my career doing particle experiments, I mentioned that, in the mid-1990s, I proposed a dream detector at the LHC that got turned down as a first-generation experiment. And so I spent about 6 months figuring out what I wanted to do next. And one of the things I considered at the time was working on climate change. But, after looking at it, I decided that the science was sound. The Kyoto Treaty had been negotiated, and so I thought there were more important things to work on. And so that's why when, I saw this incredible transformation, it was kind of a wake-up call to me. And so I came back and started, it's like, what have I missed? What's happened in the last 20 years or so? And so at the end of 2018, I stepped down as dean, and about a year later decided that I wanted to spend most of my time working on climate change, which is what I've been doing for the last couple of years. At the start of this talk, I want to make one distinction between climate science and climate policy. In particle physics, the public policy implications of the mass of the Higgs boson are not large, right? It's not going to make a big difference in people's lives, if it's a little bit heavier or a little bit lighter than it is. But issues of climate change are ones that do have policy implications. But while the science is sound, the question as to what to do about it is not a scientific question, right? It's a question of values, economics, and even a variety of other things. And I think this often gets confused in the public discussion, and so what I want to do today is talk about climate science and the interface with climate policy, but not about climate policy itself. And incidentally, if there's questions as I'm talking, don't hesitate to ask. I encourage my students to talk and try and create a lively class. So sort of the agenda, and you'll give me a warning of maybe 10 minutes or so if I start running long. Yeah. I'm gonna basically sketch for you a little later in the talk the fact that we're actually living in the midst of a large-scale geophysical experiment that was unplanned. I'm going to talk about sort of the history of climate science, the impact, sketch some of the impacts of climate change as it develops. Then I'm going to segue to the question of, what have we as a civilization put in place to try and monitor what we know about climate change on an ongoing basis and provide that guidance to policymakers without presupposing any particular policy options. And then the final thing, if there's time, that I want to talk about is issues of disinformation and the formulation of public policy. And then closing remarks. So just a statement that you'll appreciate better in a couple of minutes. We're about 70 years into a global unplanned geophysical experiment. So let me provide some background for that. So let's look at the history of climate science. It really began in 1824 with Joseph Fourier. That may be a name some of you know from Fourier's series, Fourier transforms, heat equation, and so on. And in 1824, he wrote essentially the seminal paper on climate change, roughly general remarks on the temperature of the terrestrial globe and planetary space. And in that paper, he asks the question, what determines the Earth's temperature and that of the other planets as well? And he basically pointed to three possible things that could contribute to it. One is solar radiation, and I'll talk a little bit more about that in a minute. Second thing that he considered was heat from interplanetary space. He viewed space as a medium. This was still in the period of the ether, and he imagined that ether would have a temperature associated with it. He thought this was probably likely to be fairly important, but he had no way at the time of determining it either experimentally or theoretically. At this point, we know that he wasn't entirely wrong. We're bathed in the cosmic microwave background radiation, but its contribution to the Earth's temperature is utterly negligible. And then the third thing that he considered was primordial heat from the Earth's core radiating outwards. And that was an area where, with his background in heat, he actually had done a series of careful measurements and was able to show in the paper that this was not a significant contribution to the Earth's overall temperature. What I thought was most important was the role of radiation interacting with the atmosphere. At that time, they knew about infrared radiation, which he called essentially dark radiant heat. And so he had this picture of sunlight coming in, the atmosphere being transparent to sort of visible radiation, being absorbed by the Earth's surface and being re-radiated, and that radiation then interacting with the atmosphere. And he talks in the paper in a fair amount of detail about sort of a model, literally a greenhouse, that they knew that glass would absorb the infrared radiation, and as a result, the greenhouse is much warmer than it would be. But he didn't have the ability at that time, they didn't know any of the parameters, the relevant atmospheric parameters. So about all he could do was say that in the present state of the theory and owing to lack of observations, we can't do anything quantitative. So he laid out a program of research which really we're still on 2 centuries later. He said take more precise observations, study the movement of heat in liquids and in the air, he expected that new properties of radiant heat might be discovered, and in fact they were. And these theories have a vast future ahead of them. And so, in a real sense, he qualitatively understood what was going on, and he sketched out a program to try and make it quantitative. The next big step forward was 30 years later. and it was by Eunice Foote. This is actually the first physics paper written by an American woman. And it was on the heat of the sun's rays. And roughly what she did was study the interaction of sunlight with various gases qualitatively, semi-quantitatively. And of the various things she looked at, water vapor was extremely important, and then the other one was what we now call carbon dioxide. And in particular, she concluded an atmosphere of that gas would give to our world a high temperature, and if, as some suppose, at one period, namely in the Carboniferous, the air had mixed with a larger proportion than at present, an increased temperature from its own action as well as from the increased weight must necessarily have resulted. The latter part's negligible. And this got a certain amount of popularity at the time. It was written up in Scientific American. But again, she observed that carbon dioxide is what we now call a greenhouse gas, but wasn't able to make the kind of precise measurements that would enable you to do real calculations about the impact on the Earth. So it's another 40 years before the next major step. In the meantime, physics had made, and chemistry had made enormous advances. We understood things like the Stefan-Boltzmann law, how surfaces radiate at a given temperature. Precision measurements have been made of the interactions of carbon dioxide with infrared radiation. And Svante Arrhenius, who won the Nobel Prize for Chemistry in 1903, in 1896 wrote a paper on the influence of carbonic acid, that is carbon dioxide, in the air upon the temperature of the ground. And basically the important conclusion from that paper was that you expected the mean temperature of the Earth to increase like the logarithm of the concentration of carbon dioxide in the atmosphere. And we'll come back and see that a little bit later. It was recognized during this time that putting more carbon dioxide into the atmosphere, if you increase the concentration of carbon dioxide in the atmosphere, then the temperature would likely go up. But there was a widespread belief that the oceans would absorb most of the carbon dioxide, and so that we didn't really have to worry about it. And so it was 60 years later, in the mid-1950s, following work that was enabled by the atomic testing. It enabled us to follow, basically radioactive tracers. The proportion of radioactive carbon-13 in the atmosphere changed as a result of the testing, and so you could look to see in seawater at different levels and so on how much of the new carbon dioxide that was radioactive had been mixed in with the ocean as a whole. And that led Roger Revelle and Hans Suess to write this important paper, Carbon Dioxide Exchange Between Atmosphere and Ocean, and the question of the increase of atmospheric CO2 during past decades. And when they were writing the paper, as you read it, it's clear that they started off as they were writing it up, thinking that there really wasn't anything to worry about. And then you can tell that midway through, they sort of, did the calculations, completed them, with an estimate that about 40% of the carbon dioxide that we emitted would stay in the atmosphere for times of centuries, with the result that as industrial emissions of CO2 increased, that we were entering an era of very rapid increase in carbon dioxide in the atmosphere. And this was before the days of computer word processing, and indeed whiteout had only been invented the year before. And so one of the people who's written a history of this period went back to the journal, and they still had in the archives the paper, and they had in fact over one of the paragraphs pasted a rewritten paragraph after they had reached that realization. And so the key thing there is the increase in global mean whoops, put this back. The concentration of carbon dioxide in the atmosphere increases proportionally to the amount of CO2 emitted. And the other thing they recognized in that paper was that up until that point, human emissions of carbon dioxide have been dominated by land use changes, things like burning down the Amazon rainforest and things like that. And that was going to shortly be increased by burning fossil fuels, and that was likely to grow exponentially fast. And so, as I said, that marked the beginning of what's really a global unplanned geophysical experiment. Or to quote the paper, during the next few decades, the rate of combustion of fossil fuels will continue to rise exponentially. Thus, human beings are now carrying out a large-scale geophysical experiment, and we're all living in the middle of it.
Is that the language they use?
That's literally the language they used. Yeah, that's a direct quote. Now, one of the things that was important about the timing of this was the next year was International Geophysical Year, and they were both on the organizing committee for the United States. And so one of their concerns was in this experiment that we weren't taking the data that to actually follow it. And so they managed to get approved establishing a station on Mauna Loa to monitor carbon dioxide continuously. And so that monitoring began in March 1958, a few months before I was born, and has continued ever since, so that we've actually got data for this giant experiment. So by 1958, the basic picture for anthropogenic climate change was pretty clear. Human activities in a variety of ways emit greenhouse gases, of which carbon dioxide is the most important. A significant fraction of that stays in the atmosphere. Significant fraction is also taken up by growing things and by the ocean. But order of half of it stays in the atmosphere. And that in turn, going back to Arrhenius, is going to cause an increase in the global mean temperature. And so now, 65 years on, we have data. The top graph here is human emissions of carbon dioxide measured in billions of tons of carbon per year. The sort of brownish line is that due to land use. And the blue is from fossil fuel emissions. And it was in 1958, or thereabouts, give or take a year, that the fossil fuel emissions exceeded those due to land use. Similarly, the concentration of carbon dioxide in the atmosphere, the blue is the continuous monitoring in Mauna Loa. This is actually nicely fit by a constant plus an exponential. The gray dots here are carbon dioxide concentrations measured from cores in Greenland and Iceland. Basically, as snow falls there and then gets tamped down, there's some air that's caught into it. As it gets crushed and turned into ice, it forms bubbles. You can get the bubbles and measure how much CO2 is in it. It's not as precise. It's averaged over a couple of decades effectively, but basically shows you that CO2 was rising roughly one-yearly until the late 1950s, and then the increase since then has been exponential. The dashed line here, for reference, is the highest the CO2 concentrations have been in the 800,000 years that we have. So at the warmest of the interglacials, we're just blowing right past that.
Dr. Taylor?
Yes.
What is the land use? What does that refer to?
This is things like deforestation for farms, rice paddies emitting methane and so on. So it's as agriculture has increased, we've changed the way
Cut trees down, plant.
Yeah.
Got it.
Yeah, and this is the estimates of the global mean temperature. These are compiled from all the weather data at all the weather stations, or at least those with significant records. Also draw upon ship's logs and so on. And so the task of assembling this record, has been immense, and there's a lot of interesting factors about it. But in any case, And then moving into here, we've got satellite data to corroborate it. But again, the rough picture is a slow increase, and then it begins to take off. And with the fluctuations from year to year, they're representing actual fluctuations in the climate due to things like El Nino and so on. So one of the things I think sometimes we don't do well in communications is, these plots tend to be presented as time series. But I think there's a real virtue to, so this is the total carbon dioxide in the atmosphere measured in gigatons. And this is the cumulative CO2 emissions since 1958 measured in gigatons. And what you see is a straight line. Right, if you like what Ravel and Seuss and others had thought before 1957 was that this line would be like this. And instead, about 45% of the carbon dioxide we emit goes to increasing the amount of carbon dioxide in the atmosphere. And then the other thing that, we have 65 years of data now on this grand experiment is Arrhenius's prediction, essentially, that the global mean temperature should increase like the logarithm of the CO2 concentration. And so here we have the natural log of the CO2 concentration. Here we have the global mean temperature. And, it's basically a straight line with fluctuations of about 1/10 of a degree centigrade from year to year.
Is that moving forward in time?
Roughly, it's moving forward in time, but well, yes. Actually, the CO2 is monotonically increasing here, so yes, this is moving forward in time. So this is exactly the same data as this temperature. So basically, we're plotting this temperature along here versus the log of this, and this is monotonically increasing. So you're right, it's increasing in time.
So what is the date on that, the start of it?
Oh, so this starts in, because we have the high quality CO2 starting in 1959, so this covers 1959 through 2024. I don't have the 2025 point on here, it would be about here, just a little above the red line.
So you could put another scale on the bottom that said time.
Yeah, exactly. But and maybe I should do that. I do this to emphasize that, if you just plot it linearly in time, right, it's actually slowly accelerating. The underlying dependence on CO2 concentration is linear. So the scale on here in time would not be linear. The years would be closer together down here than they are out here, is basically the point. Yeah. These are great questions, by the way. So, in a real sense, the theory as it was developed, over 130, 140 years, has basically been pretty well shown out by this giant experiment that we're part of. I'm sorry? Okay, yeah. There have been further important developments, right? This was just looking at one variable, the Earth's average temperature. The 2021 Nobel Prize was awarded in physics was awarded to Syokuro Manabe. Beginning in the mid-1960s, he and his collaborators, with the advent of computer power, began to develop steadily more detailed simulations of the Earth. Starting off in the early ones, they just had the atmosphere as 17 layers. Then they began to take into account the whole world. By the mid-70s, they had built the basis for not only computer modeling of climate, but computer prediction of weather. And so all of the weather forecasting that we use these days follows directly from his work. And then the final thing that I'll come back to again is, at this point, as I'll argue in a minute, right, these changes to the climate that we're making are beginning to have significant impact on parts of the ecosystem, and as a result have public policy implications. And so I'll describe the Intergovernmental Panel on Climate Change, the IPCC, in a moment, but it's a process by which every roughly 7 years there's an effort to assess everything that we've learned since the last report. Summarizing all of the scientific literature, trying to assess what we understand well, what we understand poorly, where we need to understand things better. The last round totaled about, the summary of what we knew was about 7,500 pages long. So there's a lot. But they do condense it down into ultimately a series of headline statements, and the first headline statement of the last one was, "It is unequivocal that human influences warm the atmosphere, ocean, and land. Widespread and rapid changes in the atmosphere, ocean, cryosphere, and biosphere have occurred." And then maybe to say a little more, the process of computer modeling now is, is a very large enterprise. There's a few dozen groups that independently are doing the same thing. But in each case, as you're simplifying the entire world to something you can run on a supercomputer in a year, different groups make different approaches to parameterizing what you can't resolve, things like that. But it also basically makes clear that it's only been sort of in the last quarter century that the signal has really moved out of the noise, right? If you're back here in the 1990s, if you did careful statistical analysis, like I was looking at in 1998, it was pretty clear that we were actually seeing what had been predicted. But at this point, it sticks out like a sore thumb. And one other point I want to make is, well, this is sort of the state of things as of 6 years ago. This kind of modeling, even with the cruder models, by the early 1980s, basically already understood this. And in particular, Exxon in 1982 had an internal scientific group working on climate change. This is a document that became public as a result of a lawsuit, I believe, by the state of Massachusetts against Exxon, claiming that, alleging that because they had withheld this information, they were effectively defrauding their investors about the risks associated with their product. But in any case, they had a 1982 internal study, and they had this diagram in there, basically sort of schematically showing what had happened in the past, and then what they expected if CO2 was a greenhouse gas as they believed, versus what would happen if CO2 wasn't a greenhouse gas and you didn't need to worry about it. And so a couple of years ago, when I was creating my introductory course on climate change, I wondered, how well did they do? And the answer is they nailed it. The blue is sort of the global mean temperature in the years leading up to it. Now, they wouldn't actually have had that data at that point with that kind of precision, but we have it since then. And the red's what happens since they had that study. And again, there's probably 3 or 4 dots that I haven't updated this on and be about here now, but they nailed it. So, as I said, we've talked so far about sort of this headline number, the annual average temperature on the Earth. So averaged over every spot on Earth, 24 hours a day, 365 days a year. But we don't experience that directly. What we experience is sort of the weather in our region over a period of time. And so I was part of a group last year that was working on regional planning for this. And one of the things I put together was a distribution of Cleveland's annual average temperature. And so the blue, coming down here through the overlap, is sort of the distribution of the average temperatures in Cleveland from 1960 to 1989, and the red is from 1995 to 2024. And what you see is that the average has moved over, as expected, where we're warming like the rest of the world. And it's also gotten kind of smeared out because the rate of warming is increasing. Basically during this period, it was very slow and it's becoming much faster. Now, you can do the same kind of analysis for any of a variety of different things. One of the ones that I like to show is average summer temperature, right? Because we all have experience with warm summers and cool summers and so on. So I guess about 15 years ago, James Hansen, an eminent climate scientist, took the temperature records from all temperate northern hemisphere weather stations in the summer. Each one of them, if you plot it, has sort of a bell curve like that. The width of them varies, right? There's not as much variation if you're next to the ocean compared to if you're in the heart of the continent. So he normalized them all by whatever the local standard deviation was, and then you can combine the results. And so this is what he found. So in 1951 to 1980, these several thousand different stations he was looking at had a curve that was roughly a bell curve, and for visual purposes, he divided it into sort of the coldest third of summers during that time, the middle third, and the warmest third, and then also the warmest 1/10%. By 1990 to 2000, the curve had visibly shifted over. You were only about 15% of the time having summers as cool as they were a third of the time back in 1951. And conversely, almost 5% of the time you were having summers that were as warm as only the warmest 1/10% back in 1951 to 1980. And then by 2010 to 2020, it shifted even further, so that the coolest third of summers in 1951, only about 3% of the time did you see summers that cool in that period, and correspondingly enormously warming on the other end. So, in terms of the shift may sound small, right? Matters of a few degrees Fahrenheit. But in terms of probability of a warm summer or a cold summer, it's a big shift in terms of the frequency that you see things or don't see things. There's also important regional differences. The Arctic, for example, a big fraction of the incoming sunlight gets reflected during much of the year due to snow and ice. As it warms, there's less of that, so that one of the things that feeds into it is increase in the amount of sunlight that's being absorbed in the first place. And so one of the upshots is that the Arctic region is warming several times as fast as the world as a whole. And in particular, parts of the Arctic and Siberia and so on are warming almost 6 times as fast as the rest of the world. So the corollary for this is the Arctic sea ice, for example, is thinning out, and the period in which much of the Arctic is ice-free is increasing fairly regularly, to the point that it's now become possible during parts of the year for ships to go through, which is, among other things, from the point of view of China, potentially a much cheaper way of getting things to Europe than to go all the way around otherwise. It also makes it more reasonable to open up these areas, or easier to open it up to for mineral exploration, petroleum exploration, and so on. And so for some time, there's been increasing expectations that the Arctic is likely to be a geopolitical hotspot. And so it's not surprising, for example, that we see increased tensions over Greenland as a result of U.S. interest, Canadian interest, European interest, Russian interest in particular, and the Chinese as well. Now, much of the analysis of climate change, basically, the underlying assumption is we're making, on the grand scheme of things, small changes in temperature, and so you expect, small effects that would be reversible if you turned it around. So that, for example, the warming of Cleveland, right, if we were to decrease the amount of carbon dioxide in the atmosphere, then you would expect things to go back to where they were before. There's parts of the Earth's climate system where there's reasons to worry that we're pushing close to the point of an irreversible change, or one that would be very difficult to reverse. And the one that's maybe most worrisome is what's called the Atlantic Meridional Overturning Circulation. And so this is kind of a schematic of the currents in the Atlantic. But the important thing is that you've got currents that take warm water from sort of the tropical regions northward along off the coast of North America, up to sort of north of much of Europe, where it then sinks with returning currents deep down. And the reason why this is important is it transports enormous amounts of heat from the tropics into the northern latitudes, and the primary beneficiaries of it are Europe. So, if you've ever looked at the latitudes of European capitals and compared them with American cities, you may find yourself surprised because they're typically much warmer than cities at a comparable latitude in North America are, and it's because of this. So back in the early 1960s, an oceanographer named Henry Stommel set out to try and understand what drove the current in the first place. And it's a delicate interplay between thermal effects and salinity effects. The warm water in the tropical regions, it gets warmed up, water evaporates, it becomes saltier. So becoming saltier makes it more dense, warming it up makes it less dense. In the north, as it cools off, then it becomes denser, and that's what drives the sinking. But what he was concerned about was that, and he's looking at salinity flow in his model. Actually, what's happening is in the northern, it's becoming, the worry is it's becoming less saline because of fresh water coming in, particularly melting off the glaciers in Greenland. But adding fresh water to it basically decreases the salinity, decreasing the density of it. And so he put together a really simple model and showed that, in fact, you have behavior something like this. So as you increase the amount of fresh water coming in the north, if you start up here, say we're here, and increase the amount of fresh water, this is the velocity of the flow. It drops slowly, and then there's a certain point in his solution, his equations, where there's no longer a solution. On the other hand, if you started with a very large forcing, you'd actually have the flow going in the other direction. You decrease the amount of fresh water coming in. It drops down, and then at a point, again, there's no solution. And then there's a region in between when there's two solutions. And so what the concern is that we are somewhere around here, headed towards this point. And if you reach that point and continue the force, and then you drop very quickly down to here. And then even if you reverse it, you don't get to immediately jump back up here. You have to go all the way back here before it would jump back up. And so this would be a rearrangement of the oceans, the currents in the Atlantic on a fairly large scale. And so he started worrying about it, and it was a simple model. It was people maybe worried a little bit. They began to worry more in the 70s, began to worry even more in the 80s, began to worry even more in the 90s, to the extent that in the 90s we began to collect some data. It's still not like the data that we would like. And that data was worrisome, and so in the last 20 years, we've begun to collect even more data, but still much less data than I think oceanographers would like. We've also developed much more sophisticated simulations that basically confirmed the picture that he had in general. And then, the question as to why you should care, if it collapsed, what you see is that significant portions of the Earth become much cooler, other regions become much warmer. There's a big pattern. Much of Europe and Asia becomes drier. Other areas become more moist. The implications, the kind of temperature change we're looking at here is average temperature change in much of Europe of maybe of the order of 10 degrees Fahrenheit. That's pretty big and has pretty big implications for agriculture and so on. So what do we know about it? We don't have nearly the data we'd like. The models are still less detailed than we would like. And so the IPCC in their last assessment, the Atlantic meridional overturning circulation is very likely to weaken over the 21st century in basically every scenario they looked at. While there's high confidence in the 21st century decline, there's only low confidence in the magnitude, and there's medium confidence that there will not be an abrupt collapse before 2100. Okay, I don't know about you, but I would be happier if we could make a stronger statement than there's only medium confidence that there won't be a collapse. If such a collapse were to occur, it would be very likely cause abrupt shifts in regional weather patterns. Now, part of the reason that I quoted this at the length I did was, one, to give you sort of our best assessment of this particular nonlinear phenomena, which we are in danger of crossing the threshold. But also to call attention to the way that the IPCC reports it, right? It's not black and white, right? It's laid out in terms of trying to assess both the likelihood in the sense of where we can make estimates, what's the statistical probability based on what we can, and also confidence based on how much data we have or don't have. How confident are we that even the way we're doing the estimates makes sense? So that the current state of climate science is not just on or off. It's 7,500 pages of measured statements with the supporting evidence. How am I doing in time? Okay.
Take all you want.
Okay. So the point is that by the mid-1980s, there was sufficient scientific, for example, companies like Exxon were confirming the academic science consensus. By the mid-1980s, there began to be a concern at the international level of needing to address it in a more systematic way. The scientific community made a recommendation that there should be an ongoing scientific body to make assessments of what we knew that would provide input to the policymakers. It was at that point that the Reagan administration entered into it, and President Reagan in particular. He had, over the objections of much of his cabinet, helped negotiate the treaty that regulated chlorofluorocarbons to address the ozone issue. And he similarly felt that the climate issue needed to be done. But he felt that it was really important that it not just be left to the scientists, that if it was going to have impact on policymaking, that the governments of the world needed to be there from the beginning. And so what I want to turn now is to those sort of questions. And so it was in 1988 that the Intergovernmental Panel on Climate Change was created, and I'll talk a little bit more about it at the moment. It was created by a unanimous resolution of the United Nations, And it had several charges, one of which was to periodically assess what we know, but also as to serve as the body that would negotiate potential future treaties to address issues of climate change. The first of these was in 1992 with the creation of the United Nations Framework Convention on Climate Change, which laid out at great length a number of principles that should be addressed to it. This treaty was signed by the first President Bush and ratified by the Senate without recorded objection. They didn't take a roll call vote, no one asked for it, it was by acclamation. That then led to the 1997 Kyoto Treaty, which was designed to address it. It set targets for addressing greenhouse gases and had essentially very weak penalties in the form of if nations didn't meet those targets, then basically they would be shamed. That was too much for the United States, and I'll talk a little bit about that a little later. President Clinton signed the treaty, but never sent it to the Senate because it would not have been ratified. And eventually, by the early 2000s, it was clear that it was not going to be a viable framework, and that led to the negotiation of the 2015 Paris Treaty, which allowed nations to set individual targets and had no penalties for them not meeting it. So in many ways, a very weak treaty, but one, the whole process depends on consensus, as I'll talk about in a little more detail. So the Intergovernmental Panel on Climate Change makes a distinction between science and policy. Through its assessment, the IPCC determines the state of knowledge on climate change. It identifies where there is agreement in the scientific community on topics related to climate change and where further research is needed. And we've seen the carefully calibrated language they use on topics like the Atlantic circulation. The reports are neutral, policy relevant, but not policy prescriptive. It basically tries to provide advice that if nations pursue different policies, what's expected to happen, but it doesn't tell you what to do. And the assessment reports are designed to be a key input. So how it works is the governing body is the IPCC plenary. It is representatives of each of the 196 nations, now 195, since we have withdrawn from it, of the world. Essentially every nation that's generally recognized and some that are disputed are parties to the treaty. Taiwan, because of Taiwan's particular legal status vis-a-vis China, is not represented as a voting member, but is represented as an observer. That's the governing body. It's divided into 3 working groups of scientists. All are volunteers, and I'll describe how they're selected a little later. And then has a very small bureaucracy. The permanent staff of the IPCC is only 17 people. And its principal task is to do these periodic assessments of what we know. And so the process is first, for each report, there's a development of an outline of what's going to be addressed. And there's a process by which the nations of the world can bring forward proposals for things that they would particularly like to have looked at. In the current cycle, technologies for directly removing carbon dioxide from the atmosphere is one that will receive special emphasis. Once that is agreed to by the nations, by consensus, then the process of author selection begins. And so each nation and the observer organizations are allowed to nominate authors. There's then a process by which they are selected and again approved by the full body. Once the group of authors are approved, they write a first draft of the report summarizing all the scientific literature for the last 6 years. That then gets sent out to a second group of scientists selected by the same process as the first, but distinct from them, to criticize, correct, and comment on the whole thing. It also gets sent to each nation, who sends it out through their individual processes for comment within the nation. All those comments come back to the first set of authors, who have to respond to all of them, though they don't have to incorporate all of them. They produce a second draft, which then goes back to all the nations of the world, that sends through the process again, and then generates a final draft. That final draft then goes to the full body. In practice, and that is the plenary, the representatives of each of the nations. In practice, they don't touch the bulk of the text, but the summary for policymakers, which is probably the only part that most people ever read. They go through line by line, figure by figure, caption by caption, reference by reference, in marathon sessions. So, for example, and everything is done by consensus. So, for example, anything that's gone into those reports has been approved by, for example, Saudi Arabia, by the major petroleum producing countries, as well as nations like Palau or Tokelau that are in serious danger of being underwater. Any changes they make have to go back to the scientists to approve it, so that the politicians aren't allowed to say things that the scientists won't accept. But there are times when there are things the scientists would like to include that there's not consensus on including and drop out. And so, as I said, the last time around was about 7,500 pages, and the conclusion was it's unequivocal that climate change is real. Now, I want to segue to a topic which I think is important in terms of how science works and in general, and the interface between science and public policy. I'll call it disinformation, and maybe I should call it trust in the formulation of public policy. So, we all grew up, I think, with a classical notion of the individual scientist doing experiments and thereby, discovering, scientific truths. But even an individual scientist, depends on the work of others to interpret, even the design of their apparatus and so on. And so there's an implicit level of trust in sort of the received scientific body at that point that's critical. Last year, when I was speaking about the particle physics experiments, right, we were talking about collaborations of several thousand scientists, each working over 20 years on a single detector. And so, up until World War II, if you look at Nobel Prizes in particle physics, the field I've worked in much of my career, they were all single authors, with maybe one or two exceptions. Then they began to grow, and the size of the collaborations that have led to Nobel Prizes in particle physics actually has been growing exponentially since the 1950s. And what that's required is, the experiment I did at Fermilab was 24 people. Me and my co-spokesman probably had a very good understanding of every aspect of it, but there were certainly large sections of the code used on the analysis, on the Monte Carlo simulations and so on, that had been done by others. We had developed internal processes to make sure that we had confidence that everything everyone did was in fact correct. In the large collaborations, it's incredibly systematized, just so that within the collaboration you have confidence that if not individually, right, in the big experiments, there's no one that understands everything. But collectively, you have confidence that you as a collaboration understand the details of everything and have ways of testing that along the way. The issues of trust become important in the broader discipline. If you're not part of that experiment, but part of another experiment, right? There's things you can do to try and validate, and make sure that what they're saying is correct. And so it's important to build those mechanisms for trust. This is also true in the larger scientific communities, right? Why scientists always need to be looking and trying to poke holes you don't expect to take things on the face of it. You try and find ways of testing so that you have confidence in what's being said. And then these issues are even more important when you're communicating with the general public, and arguably even more important when communicating with policymakers. So on issues of science that have policy implications, there are times when the question of trust and so on becomes really important. And there's a wonderful book that was written maybe 15 years ago, maybe longer than that, by Naomi Oreskes and Eric Conway at Harvard, called Merchants of Doubt. And so it looks, for example, in the context of the efforts to legislate limits on tobacco, efforts that were made to try and cast doubt about linkages between smoking cigarettes and lung cancer, and a number of others, climate change included. I want to spend a few minutes talking about an instance along this line. It was a project convened by the American Petroleum Institute in 1998 after the Kyoto Treaty had been signed, but before it was clear what was going to happen to it. They convened a group of some of the fossil fuel companies, others declined to participate, and some think tanks and so on, and created what they called the Global Science Communications Action Plan. And we know about this because someone linked it to the New York Times. That's a copy of the facts, I guess, that was sent to the New York Times. So, it's about a 20-page document or so. They laid out their goals. Victory will be achieved when average citizens, quote, understand, recognize uncertainties in climate science, recognition of uncertainties becomes part of conventional wisdom, media, quote, understands the same thing, media coverage reflects balance, and recognition of the validity of viewpoints that challenge the current conventional wisdom. Industry senior leadership understands this as well, and one of the things they're concerned about was there were a number of fossil fuel executives that, were actually taking action to address the challenges of greenhouse gas emissions. And that those promoting the Kyoto Treaty on the basis of extent science appear to be out of touch with reality. They elsewhere in it basically said that victory will only be achieved when not only have we killed the Kyoto Treaty, but there's no chance of anything ever coming back, which means our work may be never done. Their strategy was built around a poll they did. They polled 1,100 informed Americans, that being their title, which suggested that the majority of American adults in the mid-1990s believed that climate change was real and that the government should do something about it. But what they found was that when people were informed that, quote, some scientists believe there's not enough evidence to suggest that what's called global climate change is a long-term change due to human behavior and activities, 58% of those surveyed said they were more likely to oppose the Kyoto Treaty. And so they laid out a strategy of recruiting some scientists, preferably not with a climate background, training them in media relations to go on talk shows and talk radio, things like that. Started campaigns to write op-eds, generate letters, create grassroots organizations or supposed grassroots organizations to write letters to legislators and so on, and certainly were successful. Another part of the plan called for preparing educational materials for K through 12 teachers so that minimize the chance of doing anything in the future. In essence, the strategy had 2 points to it. To emphasize disagreement. People doubt science when they think the scientists disagree with each other, and therefore tell them that scientists disagree with each other. And the other key thing was uncertainty. People doubt science when they think that conclusions lack certainty, therefore tell them that conclusions lack certainty. You're right.
Is that okay?
Yeah, no, yeah. So now let me come forward to where we are now. In 2009, the Environmental Protection Agency issued a finding in which, the synopsis of it from the text of it is, the administrator finds that the current and projected concentrations of 6 key well-mixed greenhouse gases in the atmosphere threaten the public health and welfare of current and future generations. And that finding has been the basis of much of the regulatory action in the United States since 2009. Now, when President Trump began his second term, he announced very quickly his hope that the 2009 finding would be reversed. And so on July 29th, 2 documents were released. One, the EPA released a reconsideration of the 2009 endangerment finding. It's basically 78 pages in the Federal Register, summarizing the scientific and legal reasons for reversing that 2009 decision. The scientific part of it was based on a draft report released by the Department of Energy the same day, called a critical review of impacts of greenhouse gas emissions, which was 152 pages long. And the original draft rule from that time of the EPA to reverse it depended on the DOE report. The 2025 report was provided to the EPA and was reviewed and relied upon in formulating the proposal. Now, the Secretary of Energy convened the climate working group personally. The federal government has a series of regulations on how studies on major scientific issues should be addressed. Federal court later in the fall found that this process had violated that. But he convened a group of 5 well-known climate skeptics. These are not stupid people. Judith Curry is former chair of atmospheric sciences at, I believe, at Georgia State. Steve Koonin was, Georgia Tech? Yeah, okay, thank you.
What was that?
Georgia Tech, yeah. Yeah. Steve Koonin was professor of physics at Caltech and provost at Caltech, and then chief scientist, I believe, at British Petroleum. Now, the tack that they were going to take was not a surprise. Koonin wrote a popular book about 5 years ago called Unsettled. What climate science tells us, what it doesn't, and why it matters. And Judith Curry wrote a book, Climate Uncertainty and Risks, which, I think. The general strategy was that laid out by Koonin in his book. The impact of human influences, he argues, is too uncertain and very likely too small compared to the daunting amount of change required to actually achieve the goal of eliminating global net emissions by, say, 2075. Now, one of the things is right, that statement is, the evaluation that the amount of change doesn't warrant what's going to take into it is not a scientific question, right? That's a question of other values. What it's going to take, what could be reduced in some form to cost-benefit analysis. There's other ways of analyzing it, but it goes beyond pure science. The DOE report, however, is confined largely, or much of it, to the science side. Now, when it was released, and I started reading through it, I found it disingenuous, and I'll explain why. I'll give some examples in a moment. There was a 1-month period for comment on it with the DOE, and the comments were structured, every comment had to be on a particular sentence, figure, table, and so on. And so it's not a general overview. But very quickly, sort of a subgroup of climate scientists organized themselves. There were about 85 of us that dropped everything we were doing for the month of August to go through and comment in detail. The DOE report was 150 pages long. Our comment was 450 pages long, and if we'd had another 2 weeks, it probably would have been twice that. I'll give you a summary of it. The Climate Working Group report exhibits pervasive problems with misrepresentation and selective citation of the scientific literature, cherry-picking of data, and faulty or absent statistics. It does not meet the standards of quality, utility, objectivity, and integrity appropriate for use in supporting policy makings. So, to illustrate, give you a feel for the substance of the report, much of it's quite technical. But, we've already looked at the data for this grand experiment we've been on for the last 65 years. Now, these plots do not appear in the Climate Working Group report, but they do address the linkage between the top one and the second one, and the second one and the third one. And so, this is a quote from a report. Carbon cycle models connect annual emissions to growth in atmospheric CO2 stock. While models disagree over the rate of land and ocean uptake, all agree that it has been increasing since 1959.
Wow.
Now, if I hadn't already shown you the data, what would you conclude from that sentence? Yeah, the models disagree, and also the rate that the oceans are taking it up is increasing. So that sounds like a good thing. But we know what the data is, right? It's a straight line. And the disagreement of the models is some level irrelevant given the data, and second is small, right? Already Roger Revelle got it to within order of 20% back in '57. But they don't show you any of that or talk about it. They also say there's growing recognition that climate models are not fit for the purpose of determining the equilibrium climate sensitivity of the climate to increasing CO2. Now, in that graph I showed you earlier, I showed you sort of the scope of the disagreement of the models. And they also say that global climate is naturally variable on all time scales. Anthropogenic CO2 emissions and add to that variability by changing the total radiative energy balance in the atmosphere. Now, these are true statements. Right? They haven't said anything that's false. They didn't say anything false in the earlier one either. It's just not relevant. And again, right, we've seen what the data actually tells us. So, our conclusion was the Climate Working Group report exhibits pervasive problems with misrepresentation, selective citation, cherry picking of data, and faulty or absent statistics. And so it's a very subtle effort, or maybe not so subtle, depending on how well you know the subject, to undermine trust and confidence in the entire process. That's the entire point of it. So what's happened since then? The week we released our reply, the Department of Energy dissolved the Climate Working Group. So there is no group at the DOE to formally respond to it. So the report will not be completed because the group doing it no longer exists. On the other hand, they haven't withdrawn it. It's still sitting there as a draft report and is being used by, for example, a group of states' attorney generals suing for other action that goes beyond what we have time to talk about today. The EPA, in fact, in February moved forward with rescinding the 2009 endangerment finding, but for similar reasons and in light of concerns raised by some commentators about the draft report authored by the Department of Energy's Climate Working Group, yes, the endangerment finding did not depend on those for any aspect of the final action. So they essentially dropped, this is a alleged scientific prompt to the action. Now, their principal arguments are legal. Those will in fact be adjudicated. The question as to, what you think one should do about it is, as I said earlier, is not actually a scientific question, right? The Secretary of Energy has articulated a number of times that he believes climate change is real, perhaps exaggerated, but that the economic benefits of continuing to burn fossil fuel outweigh those. Those are legitimate positions that one can take in a public policy debate. But you shouldn't tie it up, in my view, with, you should try and use the best assessment of the science that you actually have, rather than gen up something designed to sow confusion. So in any case, we're in the midst of this experiment. We're not going to bring greenhouse gases to stop emitting them anytime soon. This experiment is going, even if we did, that'd be a continuation of the experiment in another way to see what happened when you did that. So this experiment will be continuing through the rest of the lifetimes of everyone in this room, and your children and probably your grandchildren. So stay tuned for that. The policy debates will continue to move forward. The U.S. has withdrawn from not just the Paris Treaty, but the UN Framework Convention on Climate Change. So we are really alone in the world. I'm sorry?
Is that good or bad?
There's a wide range of perspective, but it leaves us alone in the world at the moment.
Yeah.
Yeah. And so with that, I close. Ask if there's any questions or comments.
I have a comment.
Yeah.
I'm something that's irritating to me in all the questions and stuff, and I'm not with you on a lot of this stuff, I have to be honest.
Yeah.
But one of my concerns is that the horrendous emphasis on thinking that we can control climate and do it in an economic way has taken a lot of attention away from something that I think is a bigger issue, which is, it's partly policy and it's partly cultural. But the issue that currently worldwide energy use, we're told, expands about 2% a year. And no matter where we decide to get our energy, that's not sustainable for very long. I mean, 2% a year is doubling in 50 years and 7 times in a century. And to me, it's kind of annoying that all the discussions about other ways to make energy just perpetuates the
Well,
fantasy that we
yeah.
can.
So there's issues of timescales here. For the past few decades, the rate is, you can speak of it as being about 2% a year. The actual total energy use of humankind the last few decades has been growing more roughly linearly rather than exponentially.
What do you mean by linear?
As in linear rather than exponential with time, right? It's
Not 2%.
the amount that's increasing at the moment is about 2% a year, but it's not 2% a year on year. Now, there's reasons to worry that won't continue to be true, right? The growth of the AI data centers, for example, is certainly exponential at the moment.
The growth of Asia.
Yeah.
A lot of people over
Yeah, no, it's true, but it's still, if you look at the overall point. On the longer term, right, you're certainly right. Not on the question of decades, but certainly in the order of a century from now, the total power requirements, even if it were clean energy, two centuries from now, even on those conservative estimates would be such that even if the energy was clean, just the heat dissipated would be contributing to it.
That's the bigger, and the question, we obviously have found more fossil fuels than people thought we would 50 years ago, but there's pretty good evidence there is only so much of it.
Yeah, although there's a lot, right? What we know of is there's a lot, right? And coal in particular. But in the very long time, yeah, that's certainly not sustainable. Yeah.
Just curious, why did all the CO2 production and everything else start taking on after about 1950? Why did that shoot up so much?
No, it's just it's more or less the phenomena you were referring to. Our use of fossil fuels had been growing exponentially, but from a small level compared to the emissions we had compared to the carbon dioxide. So if you've got something that's rising linearly, and then something that's rising exponentially, if it's small below, eventually, if you wait long enough, it's going to come to dominate.
Yeah.
I mean, there's no law of physics that says it's that way. It's just a reflection of the way our economy has grown.
I have a question.
Yeah.
One of your slides, you had Cleveland temperature.
Yeah.
And you were talking about a committee or somebody.
Yeah.
So my kind of bigger question is, with that information, are there people, what are the powers that be in that area doing with that?
So,
Are they making any changes?
yeah, so the project there, so the Biden administration in the Inflation Reduction Act included several $100 billion to try and stimulate a transition to a greener economy. They also recognized that if they just pushed the money out, that there were no plans for how to spend it. And so one of the things they included was funding for states and regions to go through a planning process, and it's actually a two-stage planning process. State of Ohio, some states, Florida chose not to participate. State of Ohio participated, but focused on resiliency as opposed to action, addressing change. The Northeast Ohio area, covered by NOACA, the Northeast Ohio Area Coordinating Agency, was the regional planning process, and it was I've been part of many collaborations, and this one was one on I think trying to do it on a very short time period with lots and lots of different stakeholders, and gosh, I wish there had been like another year to do it. What it ended up doing was maybe the most important part was doing surveys of where emissions are actually coming from. It set targets that I think were unrealistic. I personally thought were unrealistic, but and then began to lay out, what are the things that you would need to do to meet them, and so the national goal under the Biden administration was to cut emissions by 2030 by 50 to 52% compared to 2005. which was certainly aggressive, but emissions have been dropping steadily in the U.S. since that time. Right, the reason they picked 2005 is sort of was at the peak. Even during the first Trump administration, our emissions continued to drop.
We had COVID too, remember?
Well, COVID
It didn't
was.
stop.
No, yeah. Well, that was a dip down that came back up the next year.
Yeah.
This is and a lot of what drove it was actually moving from coal to natural gas. For a given amount of energy, coal emits about twice as much CO2 as natural gas does, and so. But in any case. So the things you would want to do is, first of all, try and reduce the emissions going into generating electricity. That call for nuclear, for renewable, and then for shifting from coal to natural gas, things like that. That's difficult to do in this region because most of the electricity we consume isn't generated here, except what is things like Perry. Are already zero emissions. We're part of a regional consortium, and other parts of the country, I think will do better there. Here, that would be very hard on the time frame. You want to improve the efficiency of buildings. And a lot of that necessarily means retrofitting, so it's investing in better insulation and things like that. All of that would take money and would have to happen very quickly to meet the kind of goals that were in mind. The single biggest emitter in the region is the Cleveland-Cliffs steel plant, which, if I recall, is responsible for about 14% of the emissions in the region. Now, there's efforts to reduce the carbon emitted in steel processing, and Cliffs was planning to experiment with some of those at other locations. Cliffs wouldn't have been one of the Cleveland plant wouldn't have been the first one. And so, there it's like, okay, right? I mean, the only realistic way of setting those emissions to zero, say, at the moment, would be to shut it down. But then you lose all the jobs, you lose the economic activity, and it's just going to get taken up somewhere else. So that's not necessarily
Yeah, you wouldn't be shutting it down, you'd be transferring it because you'd
Yeah,
be buying it from China.
Yeah.
It's a wash.
Yeah.
And what about concrete? Concrete
Yeah.
produces tremendous.
Yeah, it sure does. Yes. Yeah, absolutely. Yeah. There were a series of recommendations, but in the end, there was no way, short of assuming that we could bring on, as yet non-existent process for removing carbon dioxide directly from the atmosphere at a suitably low cost in order to make to achieve the goals.
Dr. Taylor?
Yeah.
Can I ask you a question?
Yeah.
I've been hearing whispering from the current administration, it's just whispered
Yeah.
because they don't want to say it too loudly, about nuclear. And what do you think our chances are of increasing our nuclear capacity for generating energy in the next 20 years?
20 years is probably an aggressive timescale. There's going to be a lot of efforts towards it, but
I mean, I envision gray-haired ladies chaining themselves to trees.
Yeah.
And, you laugh about it, but I know it's going to happen.
Yeah.
And they put it in I don't want it in my neighborhood.
Yeah.
You put it over in, over there.
But
Yeah.
would that get us out of the problem? Let's answer that question first.
well,
Reduce CO2.
So for example, France, for example, depends very heavily on nuclear, right? At a time when we made the decision to to move away from it, they continue to invest heavily in it. And so the result is they've got.
Thank you.
Do you think they're, you think they will accept nuclear? I mean, even in this next 4 years, 3 years, whatever,
No,
will they build any plants anywhere?
no.
Well, at the moment, it's still difficult to build plants that fast, but I do believe some will be, on track.
But how about these modular units, small units and so forth? I don't.
Yeah, those, I've not looked at them as closely as I should, but I'm skeptical that even under the best scenarios, they're going to come on fast enough. Yeah.
I have a
That's okay.
question.
Yeah.
Are there any solutions to that excite you? Are there any like innovative sort of ways to remove the carbon? Is there anything that you think of as a positive?
I think it's just I think it's a mixture of everything. There's no magic bullet, right? In some regions of the world, some things will make more sense than others. In general, I think we should be pushing renewables and development of batteries more than we are. The progress there actually in places like Texas, for example, over the last couple of years, I think has been, truly astonishing. The rollout of solar, maybe not so surprising, right? It's been on a clear sort of Moore's Law type exponential growth for a while. But the drop in price of sort of industrial scale battery storage as backup has been pretty amazing. So that it has enormously increased the resilience, for example, of the Texas grid in summertime, which a couple of years ago, every year was a disaster, and last year wasn't, and it was mainly because of the amount of solar plus batteries they deployed.
What about fusion?
So fusion is
Yes, fusion is, and Dr. Taylor would be happy to answer your question, perhaps at the back of the room. This is stretched on longer than what we anticipated.
I apologize. Yeah.
No,
And we do have other business.
Thank you.
plans.